Next is number 43. For number 43, it states, the motor in a toy car is powered by 4 batteries in series which produce a total EMF of 6 volts. The motor draws 3 amps and develops a 4.5 volt back EMF at normal speed. Each battery has a resistance of 0.1. What is the resistance of the motor? Okay, so the batteries are in series, so the total resistance for the batteries is going to be 4 times 0.1, or 0.4 ohms. And the current is going to be equal to the net voltage, which is 6 minus 4.5, divided by the sum of the resistances. And the sum of the resistances is going to be equal to the voltage, the net voltage, divided by the amperage. So 1.5 divided by I. And the resistance of the motor is going to equal 1.5 divided by 3, which is the resistance of the motor, minus the calculation over here, which is 0.4. So the resistance of the motor is going to equal 0. This is 0.5 minus 0.4 is 0.1 ohms. 45. Now with 45 we move into a new section. The new section has to do with transformers. And there's 2 key relationships. First of all, you have what's called the primary and the secondary. And the primary is where the voltage comes in, the secondary is when it comes out. And a step-up transformer increases the voltage in to the secondary. And so you have a situation like this. The voltage comes in, this is the primary, and the voltage goes out, this is the secondary. And if the voltage over here is greater, it's called a step up, and if it's less, it's called a step down. Now I'm showing the number of turns because it's the number of turns that changes it. So the number of turns in the primary divided by the number of turns in the secondary is equal to the voltage in the primary divided by the voltage in the secondary. It's a very straightforward relationship. And the amperage of the two, because the relationship here is directly related, is actually opposite. So these are the 2 relationships that you have to know. First of all, it's primary to primary, secondary to secondary here, but it's primary to secondary, secondary to primary here. So for number 45, it states that an American traveler in New Zealand carries a transformer to convert New Zealand's standard 240 to a 120, which is standard in America, so that she can use some small appliances on her trip. What is the ratio of the turns of the primary to the secondary? Okay, for the first one, you're going what you want. You have the ratio here is going to equal 240 divided by 120. So the primary to secondary ratio here is 2. The second part of this is, what is the ratio of input to output current? Well, current is the opposite, so it's going to be opposite here, so it's going to be 1/2. And then it says, what do you do if you go back, if you're from New Zealand and you go to the United States? You just reverse this, and it steps it down from, or steps it down from a need of one, or steps it up to from a need of 120, from the primary of 120 to 140. But the key here is the ratio is inversed. If you go from New Zealand to the US. Number 48. Number 48 states, the plug-in transformer for a laptop computer puts out 7.5 volts and can supply a maximum of 2 amps. What is the maximum input current if the input voltage is 240? Assume 100% efficiency. Okay. The same ratios are up here. So the primary is equal to the secondary times over VP. And you can just look at this and see how you can rearrange this to get this. Then you put in the answers, which is 2 amps, 7.5 for the secondary, and 240 for the primary. So the primary input current is 0.063 amps. Number 48b says, if the actual efficiency is less, would the input current need to be smaller or greater? Well, it would need to be greater because any impact on efficiency would lower this number. And so to get this same output, you'd have to increase the power. A large power plant generates electricity at 12,000 volts or 12 kilovolts. Its old transformer once converted the voltage to 335 kilovolts. The secondary of this transformer has been replaced, so now the output is 750 kilovolts for more efficient cross-country transmission. And that's actually how it works. What is the ratio of turns in the new secondary compared to the old secondary? Okay, so we know that NS over NP is equal to VS over VP. And we also know that NS prime over NP is equal to VS prime over VP. This being the new voltage output and the new number of terms needed. And if you rearrange this algebraically, you get NS prime over NS is equal to VS prime over VS. And you can just fool around with this until you figure that out. I would recommend cross multiplying here. Okay, so if we put in 750 kilovolts and 335 kilovolts, then the ratio, if you do that, is 2.2. So that means the number of turns, whatever the number of turns here was, you have to have 2.2 times as many here to get that same answer. B looks at amperage. So you have IS prime over IS is equal to VS over VS prime. Remember that this relationship is inverted, which is why these are different. So you have 335 over 750. So the ratio of the amperage decreases by 0.45. What effect is that on power? P is equal to I squared R. So P prime over P, so the new P over the old P, is going to equal I prime squared over I squared. So it's going to be a squaring of this ratio, which means it's 0.2. The last two problems look at inductance, and the key here is that the inductance is equal to E delta T over delta I. And so if we look at problem number 55, two coils are placed close together in a physics lab to demonstrate Faraday's law of induction. A current of 5 amps in one is switched off in 1 millisecond, inducing a 9-volt current in the other. What is their mutual inductance? M. So if we put this in, it was 9 volts times 1 millisecond is 1 times 10 to the minus 3, and 5 amps was the change in current in that time period. And so we get an answer of 1.8 times 10 to the minus 3 henries, which is the unit for mutual inductance or inductance, or 1.8 millihenries. 57, so this was M, mutual inductance. L is just plain inductance. So E is equal to L delta I over delta T. And a 5 amp current through a 7.5 millihenry inductor is switched off in 8.33 milliseconds. What is the EMF induced opposing this? So here's the EMF. So we just plug in the numbers here. So it was 7.50. This thing does some weird things sometimes. Times 10 to the minus 3 times, and the current was 4 amps, and it was 8.33 milliseconds. And so the induced current is 3.60